Welcome to Math TV with Professor V. In this video, we're going to look at infinite limits. And we'll begin our discussion by considering the function f of x equals 1 over x, which is graphed right here. So let's see if we can evaluate the three limits that we have written off to the side. The first one is the limit as x approaches 0 from the right of 1 over x. So when we're approaching 0 from the right, what you can do is just imagine that you're walking on the graph and you're walking on the right side of 0 and you're getting closer and closer to x equals 0. So the limit we can observe is wherever the function is heading, what y value are you approaching as you move towards x equals 0 from the right? So what is 1 over x, or what are the y values approaching? Well, we notice that they're getting larger and larger. In fact, they're approaching positive infinity. So we write that this limit is equal to positive infinity. You don't have to put the plus sign, but I like to because it reminds me that I actually thought about it and distinguished which direction we're heading. Now, just to be clear, infinity is not a number. We're not treating it like a number. And technically, this limit does not exist because the function is not approaching some finite value, right? It's getting arbitrarily large in the positive direction. However, if we can pinpoint that indeed the function approaches either positive infinity or negative infinity, we do write that as our final result. You wouldn't write does not exist for this particular case, okay? Good. Now let's look at the next limit, the limit as x approaches 0 from the left of, again, 1 over x. So this time, imagine you're walking on the graph, you're getting closer and closer to 0, but you're walking on the left side of 0. So you're on this portion of the graph. Where are you going as you get closer and closer to 0? You're sliding down that hill. Whee! So you're actually approaching, in this case, negative infinity, right? Good. And then notice the last limit here is the limit as x approaches 0, and we're not specifying from which side of 1 over x. So remember, when we're evaluating two-sided limits, we have to make sure that the limit from the left is equal to the limit from the right. And they're not equal in this case. Notice, as x approaches 0 from the right, 1 over x approaches positive infinity. And when x approaches 0 from the left, 1 over x approaches negative infinity. So for that reason, we say that the limit as x approaches 0 of 1 over x does not exist. All right? Good. Now, one thing that we can observe that you probably remember from your precalculus days is that x equals 0 is a vertical asymptote. And there's ways that you probably learned how to determine where vertical asymptotes were in pre-calc, but now that we're in calculus, we're going to use limits in order to establish this fact. So now we have a new definition here. We say that the line x equals a is called a vertical asymptote of the curve y equals f of x if at least one of the following statements is true, and more than one may be true. Basically, as you approach some number a, and it could be either from the left side, from the right side, or two-sided limits, if your function approaches either positive or negative infinity, then you have a vertical asymptote in your graph. Okay? Good. So we're going to look at some more examples graphically, and then we're going to see how to evaluate infinite limits algebraically without using graphs. There's a way, don't you fret. So next function we're going to look at is f of x equals 1 over x squared, which is graphed here. Notice the only huge difference between this function and 1 over x, obviously it's growing at a little bit of a different rate because of the x squared, but also x squared is never negative, so both portions of the graph lie above the x-axis. Beautiful. So let's see here. What is the limit as x approaches 0 from the right of 1 over x squared. All right, so imagine you're going for a stroll on the graph. You're on the right side of 0. As you get closer and closer to 0, remember the limit represents what the function is approaching, what y value you're getting closer to. Where are we headed? Up to positive infinity. That's right. Okay. What about if we approach 0 from the left this time? So say you're walking on the graph, you're on the left side of 0, and you're getting closer and closer to x equals 0. Remember, the limit is where the function is going. Where are the y values headed? Where are you walking towards? Towards positive infinity again. All right. So now when I look at the two-sided limit, what's the limit as x approaches 0? And we don't specify from which side. Well, now I can say that this limit is positive infinity, because notice in this case, the limit from the left side of 0 is equal to the limit from the right side of 0. Both of them are positive infinity. All right. So we typically reserve writing does not exist when the limit from the left doesn't match the limit from the right in these kinds of situations, okay? Some textbooks, anytime the limit is infinity or negative infinity, will write does not exist in the back. I don't let my students report that as their final answer because we want to be more specific and identify in which way the limit doesn't exist if we can. All right, so just make sure you check with your instructor what they want you to do. So, how are we going to evaluate these limits without having to graph every single problem, right? Because these were pretty basic graphs that we were able to do, but we want an algebraic method. So what I want you guys to keep in mind is anytime the numerator of your function is approaching some non-zero constant, in this case, all of the numerators were 1s, right? Which is not 0, cool. And the denominator is approaching 0, that means your limit or your function is going to either approach positive or negative infinity. Or it may not exist, right? If the limit from the left doesn't equal the limit from the right. You have to investigate. But here's the idea. If the denominator is getting arbitrarily small, that means you're dividing by numbers that are getting smaller and smaller and smaller. So what happens to your overall expression, this quantity here, it's going to get bigger and bigger and bigger. It blows up. It's just up to us to figure out, is it blowing up in the positive direction or is it blowing up in the negative direction? And sometimes for two-sided limits, the limit will not exist if the limit from the left isn't the same as the limit from the right. Okay. Now notice here I wrote a non-zero constant in the numerator, because if the numerator approaches 0 and the denominator approaches 0, this is what we call an indeterminate form. And so the method for evaluation that I'm going to show you right now does not apply. You need to evaluate the limit using other methods. So I'll link some videos here where I show how to deal with these indeterminate forms. Just be careful, depending on what phase you are in the semester, whether or not you're allowed to use L'Hopital's rule. Okay, check with your instructor. If it's the first half of the semester, I don't let my students do it, only at the end. Okay, so we're going to look at the same limits that we just considered, but this time, no graphs. We're going to try to do it algebraically. Here we go. So example 1, we have the limit as x approaches 0 from the right of 1 over x. So look here, the numerator is approaching a non-zero constant. It's actually not going anywhere. It's already just a positive constant 1, okay? And the denominator is approaching 0, but from the right. So that means the denominator is positive, right? If we're from the right side of 0, we're approaching through positive values. That means I have a positive quantity in the numerator, positive quantity in the denominator. So this expression is positive. And since the denominator is shrinking, right, then we know that the whole function, 1 over x, is blowing up, getting really, really big in the positive direction. So this limit is positive infinity. You can do it without the graph. Next one, limit as x approaches 0 from the left of 1 over x. Again, numerator positive, non-zero constant. Denominator approaching 0, but from the left, so that means the sign of the denominator is negative. Think about it this way. You're approaching 0, but through values that are smaller than 0, just a wee bit. Negative 0.01, negative 0.001, etc. So you have a positive in the numerator, a negative in the denominator. This expression is getting arbitrarily large, but in the negative direction. So this limit is negative infinity. And then last limit here is the limit as x approaches 0. Notice it's a two-sided limit. We're not specifying from which side. So we have to check. Does the limit from the left side of 0 equal the limit from the right side of 0? No, it does not. So now we can write this limit does not exist. And you guys, I didn't put equals does not exist because this limit doesn't equal anything. Okay? Don't put an equal sign when it's DNE. Okay, I think we got the hang of it. Let's look at some more involved examples, all right? Get you warmed up in case you have some homework or a test coming up. Example 2. We've got the limit as x approaches 5 from the left of 2 over x minus 5. All right, so as x approaches 5 from the left, notice the numerator is just a constant. It's not going anywhere. 2, that's positive. And then 5 from the left, that means you're coming from values just a wee bit smaller than 5. So think 4.9, 4.99. So 4.9, 4.99 minus 5, this is going to get close to 0, but from the left, right? The sign of the denominator is going to be negative. So that means we have a positive quantity in the numerator, negative quantity in the denominator. So the sign of the overall expression is going to be negative. And it's getting arbitrarily large, right? Denominator is shrinking, numerator is approaching a constant. So this is going to approach negative infinity. Okay, let's see what happens from the other side. So now we're looking at the limit as x approaches 5 from the right. So again, 2, that's just a positive constant, numerator's positive. If we're approaching 5 from the right, then we're coming from values just a smidge larger than 5. Think 5.1, 5.01. So if you take 5.1 minus 5, 5.01 minus 5, this is approaching 0, but through positive values from the right. So the sign of the denominator is positive again. So the numerator, non-zero constant, denominator approaching 0, but from the right. So this limit's going to be positive infinity. All right, good. And then last one is the limit as x approaches 5. I'm not specifying from which side, of 2 over x minus 5. And as we saw, the limit from the left side of 5 does not equal the limit from the right side of 5. So this means this last limit does not exist. Okay, lovely. If we were to graph 2 over x minus 5, that means x equals 5 is a vertical asymptote. And then you probably remember from pre-calc, when you would find vertical asymptotes, you would look for wherever the denominator was 0, right? After you simplified your function. So that's where it all comes from. Okay. A little bit of a different twist here. We have the limit as x approaches 6 of x plus 6 over x minus 6 squared. Notice in this case, it's a two-sided limit. I'm not saying whether or not we're approaching from the left or right side of 6. So we're going to have to think about that. As x approaches 6, let's see what's going on in the numerator. 6 plus 6, whether or not we're approaching from the left or the right, the numerator is going to be positive, right? Whether you approach from 5.9, 5.99, or 6.1, 6.01. Those are both positive. If I add 6 to it, we're still in the positive zone, okay? Very good. And then notice again in the denominator, as x approaches 6, 6 minus 6 is approaching 0. But since we're squaring that quantity in the denominator, it's always going to be approaching 0 through positive values. So I don't really need to worry whether or not it's from the left or the right. I know the sign of the denominator will always be positive. It's just shrinking and getting closer and closer to 0 as x gets closer and closer to 6. So we have a positive quantity in the numerator, positive quantity in the denominator, which means this limit is, positive infinity. You can just write infinity, but like I said, I always write the plus sign because we have to take into consideration the sign. So I want to just reassure myself that I thought about it, okay? Good. Let's look at some more with a numerator that's a little more spicy. So we've got the limit this time as x approaches 5 from the left of x plus 1 over x minus 5. So let's see here. As x approaches 5 from the left, notice the numerator x plus 1, that's not approaching 0, right? So it doesn't really matter whether we're approaching from the left or from the right, to be perfectly honest. But anyways, so 5 from the left, you have like 4.9, 4.99, blah, 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 plus 1. The numerator is approaching 6. Either way you slice or dice it, the numerator is positive, okay? Now let's look at the denominator. We're approaching 5 from the left, so that's 4.9, 4.99. This expression, x minus 5, is approaching 0, but from the left, right, through negative values. So the sign of the denominator is negative. So positive quantity in the top, negative quantity in the denominator, approaching 0. What's this limit going to be? That's right, negative infinity. Okay, then let's look at part B, the limit as x approaches 5 from the right. Again, the numerator is still approaching 6, so the numerator is positive. That's a non-zero constant. As we approach 5 from the right, the denominator is going to approach 0, but this time through positive values because you're coming from the right side of 5. So think 5.1, 5.01. So the denominator is positive as well. So we have positive over positive. This is going to be positive infinity. Okay, good. Then last limit here, as x approaches 5 of x plus 1 over x minus 5. Well, notice again, the limit from the left side of 5 does not equal the limit from the right side of 5. So this does not exist. All right, fabulous. I have one more similar example, but I want you guys to try it. So go ahead, pause the video and see if you can complete example 5. Okay, I hope you paused the video. Did you give it a go? All right, do we remember the graph of e to the x? If not, get it burned in your brain immediately. Okay, you're going to need it for the rest of your math career. E to the x. I mean, the most important thing you need to remember is that it goes through 0, 1, 1 comma e, and then you've got a horizontal asymptote. Y equals 0. Okay. What's important about that here? Well, e to the x is never negative. Okay, so it doesn't matter what you plug in for x, e raised to some number will not come out to be negative. So I know the numerator is always approaching some positive number. And then x is approaching 3 from the right. Okay, so a little bit bigger than 3. So this is going to approach 0 from the right. I'm raising it to the 5th power. Since that's an odd exponent, it's going to stay positive. So I have a positive over a positive, denominator shrinking. So this limit's going to be positive infinity. Did we get it right? I hope so. Okay, next one. This time we're approaching 3 from the left. So e to the x, that's approaching some positive number. X minus 3, this time this is approaching 0 from the left. Since we're raising that to the 5th power, it's going to stay negative. So the denominator is negative. It's shrinking though, it's approaching 0, which means this overall expression is blowing up. It's getting arbitrarily large. So if the denominator shrinks, goes to 0, and the numerator just approaches some number not 0, right? That means the whole thing's getting very, very big. And this limit would be negative infinity. And then part C, we can see the limit from the left did not equal the limit from the right. So the limit as x approaches 3 of e to the x over x minus 3 to the 5th does not exist. Lovely, lovely, lovely. Now, if you have done some exercises in class or in your homework where you made a table of values to investigate a limit, that's fine for you to just get a feel for where things are going. But as far as finding a limit and reporting an answer and showing work, that's not acceptable. Okay, you need to be able to do it algebraically. All right, I have a couple more spicy ones. We have the limit as x approaches 3 from the right of the natural log of x squared minus 9. Now, before we can work on this limit, we have to recall the graph of y equals the natural log of x. Remember, natural log of x and e to the x are inverse functions. So when you're graphing them, you can just interchange x and y coordinates, and the asymptotes also will switch. So what does that mean for us? We just graphed e to the x, right? And I told you there was a horizontal asymptote y equals 0. So that means ln of x has a vertical asymptote right here at x equals 0. It also goes through the point 1, 0. And e comma 1, but you don't need that so much for this problem. So here's the graph of ln of x. Very crude graph, but it'll do the job for this limit problem. And the one thing I want you to keep in mind is domain is from 0 to infinity. Okay, the graph is not defined for x less than or equal to 0. So when you're talking about limits in this case, we have to be super careful that x can only approach 0 from the right side. Otherwise, we're not in the domain of the function, and this doesn't even make sense. It's not a well-defined limit. So let's take a second, use the graph. It's totally cool. Use the graph right now. Let's figure out what the limit is as x approaches 0 from the right of ln of x. Okay, so we've gone on a stroll. We're walking on ln of x, having a good old time, and we decide to get closer and closer to 0. We're on the right side. Where are we headed, people? That's right, we're going to negative infinity. This limit will come up so much over and over and over. So make sure you have the graph of ln of x burned in the brain and you understand this limit. All right? Now we can do example 6. So the limit as x approaches 3 from the right of the natural log of x squared minus 9. So what you can do, you can think of it as you're going to pass the limit inside and figure out where is x squared minus 9 approaching as x approaches 3 from the right. So approaching 3 from the right, we're coming from values just a smidge larger than 3, 3.1, 3.01. When you square it, it's bigger than 9, and then we subtract 9. So x squared minus 9 is going to approach 0, but from the right. Do you agree? It's very important that we specify from the right, otherwise we just can't do this problem. So then, now I'm going to say, okay, what is natural log approaching if x squared minus 9 is approaching 0 from the right? So now it just reduces to the same problem that we looked at here. As x approaches 0 from the right, what is the limit of ln of x? Correct, it's negative infinity. So there's really not a ton of work to show on this example. Just identify x squared minus 9, the argument, approaches 0 from the right. And then you need to know the graph of ln of x, okay? Your teacher cannot have to keep showing this to you over and over. Frankly, you have to just be responsible and learn the basics to do your calculus. All right, let's do one more. Why not? The limit as x approaches 0 from the right of 1 over x minus ln of x. So as x approaches 0 from the right, 1 over x, where's that going? Well, we did that a bunch of times. X is approaching 0, but through positive values. 1 is a positive constant in the numerator. So this is approaching positive infinity. And then we have minus, so I'm just bringing down this minus sign here, ln of x. So as x approaches 0 from the right, where's ln of x going? Negative infinity, right? We showed that right here. Okay, so I have the first term approaching positive infinity minus negative infinity. Those signs are going to cancel out. So I have infinity plus infinity. Wonderful, wonderful. So then this limit's going to be positive infinity, okay? Now, be super careful because infinity minus infinity is not 0. This is another indeterminate form. And there's several ways to deal with it depending on what sort of limit you're looking at, okay? So if you're allowed to use L'Hopital's rule, you may need to rewrite it. I'll link a video here so that it's a quotient and you can apply L'Hopital's rule, or other things. If it's early in the semester, then if you have radicals, you might try multiplying by a conjugate or doing some other tricks, okay? There's all sorts of ways to deal with these indeterminate forms. So basically your infinities have to be going in the same direction for you to be able to evaluate the limit. Like negative infinity minus infinity, yeah, that's going to negative infinity. Or positive infinity plus positive infinity, that goes to positive infinity. But the problem with infinity minus infinity is that we don't know which infinity is growing faster. Is it the first one? Is it the second one? Or are they growing at about the same rate? Because this limit may end up being 0, it might, or it might end up being some other constant, or it might be infinity, or it might be negative infinity. That's why it's called indeterminate, because we cannot determine the way it's currently written. We have to use some other methods of evaluation, all right? Doesn't mean it doesn't exist necessarily. It just means you got to bust out some other tricks. Anyways, not to get off topic because this video is on infinite limits. So I just wanted to really hone in on the quantities that approached infinity, negative infinity, and the like. But more limit videos to come, and I'll link a few here that I've already recorded. Give this video a thumbs up if you found it helpful. And as always, please send me any requests for topics and future videos that you may not be able to find on my channel yet. Please subscribe if you haven't already, and happy studying.